Alright, so we're now looking at one sample inference about a mean. And so this video is about what the t-distribution is. We're going to try to understand first why this t-distribution is going to show up. So in our previous unit, we learned about the central limit theorem. And the central limit theorem told us that under certain conditions, which of course we discussed in that set of notes, we would be able to use the following. We could then say that our y bar would be approximately distributed normally with a mean of mu and a standard deviation of sigma over the square root of n. So this is our mean of y bar. This is our standard deviation of y bar. And then, because of that, we were able to use our z formula, which was y bar minus mu over then sigma over the square root of n, and we could use that to find probabilities. Now, there's a little bit of a problem with this formula, and we're going to talk about what this problem is and why it's a problem. The problem is actually the standard deviation, so knowing sigma is actually the problem. So to understand why this is a problem, let's talk about generally our goals when we do inference. So when we do inference, there's been two different things we have talked about. We've talked about doing a hypothesis test, and we've talked about doing a confidence interval. So let's talk about those two different ideas. So when we perform our hypothesis test, we will have an idea for what to use for our mean. Why will we have an idea of what to use for the mean? Well, we'll have a null hypothesis which will have some mean inside of it. So that seems pretty reasonable. But of course, since it's in our null hypothesis, we are actually unsure of this number. Otherwise, we wouldn't be doing a hypothesis test. If instead we construct a confidence interval, we don't actually know mu. Why don't we know mu? Because that's actually our goal of what we're trying to find. As the whole reason we do a confidence interval is to estimate some number, so mu is going to be what we're trying to estimate. Now, what might seem a little strange here is I'm talking about how sigma, our population standard deviation here, is the problem, but here I'm all discussing the mean. So let's talk about why that is actually now the problem. So if we are uncertain of mu, and of course mu is our mean, we definitely don't know our standard deviation. Now, why would we not know that? Well, our standard deviation, right, is our typical distance from the mean. So if I don't know the mean, I can't know my typical distance then from that mean. So there's our problem. So what are we going to do? So let's look at what we had. So here's our formula that we had. Now I'm going to change it a little bit. I'm still going to use my y bar. Also use this idea of knowing a mu, but instead of sigma, I'm going to use S. Again, remind ourselves what S is. Right, this is just our sample standard deviation. So I hope that seems like a pretty reasonable replacement, as I'm just going to take sigma, which I don't know that population standard deviation, replacing it with a sample standard deviation seems pretty reasonable. But as soon as I do that, this thing is no longer called AZ, it's actually what's called AT. Which then probably begs the question, what's T? How is it different from a Z? How is it similar to a Z? So that's what we're going to talk about here next. So let's talk about what the T distribution looks like, and we're going to start by drawing our Z picture first. So let's kind of draw our Z here. So my Z is going to be in black. So this will be my Z. Remember something we've learned from before, Z is always centered at 0, since the mean is 0 standard deviations from the mean. Now let's draw a T. So now that you have your idea of what Z looks like, what T is like is basically a sat on Z. I'm going to give myself a little point here for reference. So that's what T is going to look like instead. So here are things that are true about it when I'm comparing the two. So T is symmetric and unimodal, just like Z. Okay, so that's one thing that's true. T is also centered at 0. Like our Z as well. So there's no difference here so far. What is different, T has a larger spread than Z. That's kind of why I describe it as a sat on one. So it's still centered, that peak is at the same place, it's just a little bit lower, and therefore it's kind of squished out the rest of the picture to have a larger spread than Z actually did. But more specifically about this spread is that the spread is actually dependent upon something. And then this spread changes based upon our sample size. I hope that idea makes some sense, because if I go back to my idea of what I'm doing here, right, I'm taking this population standard deviation and I'm replacing it with a sample standard deviation. So this, of course, sample standard deviation is coming from my data. So if my data is 5 observations, or if my data is 500 observations, I'm going to trust numbers when my sample size is 500 a lot more than I'm going to trust a number if my sample size is only 5. So this spread really is changing based upon kind of how much trust am I able to put into this standard deviation that I'm getting. So as we start working some things inside this set of notes, when we're drawing this T distribution, it's not really going to feel real different here for us. So the big moral to take away as kind of why we're using this is when I use my sample standard deviation, instead of my population standard deviation, I'm going to have a t instead of a z. So as we're going to start doing hypothesis tests, as we're going to start doing confidence intervals, things are going to follow a very similar process, but now we're going to have this new distribution that we need to talk about how it's going to change things a little bit. It's not going to be a dramatic change, it's just going to be a little change.